Okay, so last time we were dealing with that, and we had computed the grand canonical partition function that looked like this. Where we had said that Z has to lie between 0 and 1. And then we had found the average number of particles in the system that was equal to energy was summation of P NP, and this one was NP. We also have written down an equation for pressure times volume that was equal to kBT times minus kBT times summation over P log of 1 minus Z to the power minus beta epsilon P. Okay, this is all we have done yesterday. So today what we are going to do is, so first of all, we will go to the thermodynamic limit. Then we know we had done this yesterday in the first class. What happens in the second class? What happens when you go to the thermodynamic limit? That is, you make the number of particles larger and larger. You make the volume larger and larger. And in doing so, you keep the density fixed and finite. And basically, what one has to do in order to treat such a case is to replace all this summation by. Okay, so let us do it one by one. So let us first deal with this guy. So you remember that if you had summation over P, then basically.
Okay, I found this on the web for if you have, check it out.
Sorry, what is it? Okay, some sound came in. Okay, summation over P, that needs to be replaced by V divided by 4 pi square 2m by h bar square whole to the power 3 by 2 epsilon to the power half d epsilon. This is what one has to do. So this we are done. How to replace a discrete sum by an integral. So now we do it one by one, first here and here and here and so on. And let's see what do we get. If I do this replacement here, and by the way, this is what we were calling this whole factor This is what we were calling G epsilon yesterday, the density of states. So if I do this here, this was n average. So I get n average is equal to integral G epsilon d epsilon G epsilon and d epsilon divided by. So I divide out by this guy, so I get 1 by z e to the power beta epsilon minus 1, 0 to infinity. But I have to be careful now as to what happens when epsilon p itself is 0. That is when I'm in the ground state. So when I'm in the ground state, so this factor e to the power minus beta epsilon p, that becomes 1. Okay. So I have a term, so z by 1 minus z for the ground state. And since z itself can lie between 0 and 1, uh, it itself can lie between 0 and 1. So therefore, I have to be careful in taking out this term separately. Why do I take out this term separately? Because this term appears in this summation formula. This is the term here for epsilon p equal to 0. And if epsilon p is equal to 0 and z is very close to 1, then this term itself is diverging. It's a very, very large contribution. And in fact, it diverges. So that cannot be contained in the integral. So you take out that term separate. See, this problem wasn't there for ideal Fermi gas, because for ideal Fermi gas you had a plus sign. That's one. And secondly, for ideal Fermi gas, Z did not have any like allowed range of values. All values of Z were allowed. But in the case of ideal Bose gas, Z has a particular allowed range of values. And in this range, if Z is very close to 1 and I'm in the ground state, this term or this term it diverges, so I better pull it out of the integral and write it separately. That's what I've done there. Okay, so this is that. Then if I have to now look at the density n, which was in average by v, so that would simply be 1 by v times 1 by 1 by z minus 1 plus this term 1 by v of 0 to infinity g epsilon d epsilon divided by 1 by z e to the power beta epsilon minus 1. So this is the expression for the number density. Now let us look at the expression for this guy. What happens when I replace this summation over p by an integral when I go to the thermodynamic limit? Achha, one thing that we should note, and this we will come back to when we discuss Bose-Einstein condensation later in the day, that this term is finite. So long as this term is finite, okay, So then, if this term is finite as z approaches 1, z has got this particular limit, z lies between 0 and 1. When z approaches 1, if this term is finite, then this is finite, and I have to then take into account the fact that this term diverges. So I have to take into account, how do I take into account that this term is diverging? That will manifest in the Bose-Einstein condensation. So that we will discuss later in the day. But for now, you just remember that this is the expression for the density of particles in terms of the various quantities, Z and so on. Now we come to this expression, PB is equal to KBT. How does it look like when I go to an integral formulation? So this is quite easy to do. So PB by KBT, that would be equal to minus, and again this I apply that formula. So what I have to do is I have to do this one. G epsilon D epsilon log of 1 minus z d to the power minus z epsilon. But again, that same problem will appear, that when epsilon p is 0, that is, I am in the ground state. Okay, so this term it would be like 1 minus z. And when z goes to 1, so 1 minus 1 is 0, and log 0, so again we will have an infinity. So you better take it out of the term. Okay, so therefore you take out that term, and so what you get is minus of log of 1 minus z. This is the ground state contribution. This is the ground state contribution. This is the ground state contribution. As you can see, these terms are negligible unless z becomes very close to 1. If z is not close to 1, then you can, this is just a small term, small contribution. I can make that. Well, let's say z lies between 0 and 1. Let's say z is equal to 0.5. So 1 minus 0.5 is 0.5. So log 0.5, that's a small number that I can forget about. Unless z approaches 1, and then it becomes infinite. Similarly here also. And the last thing is this energy expression. How does it look like? The average energy. Average energy in terms of momentum, it was like this. To the power minus beta epsilon 3 epsilon 3. This was the expression for the average energy. So if I divide out by everything, the numerator and the denominator, by z e to the power minus beta epsilon p, I get this expression. Summation of the p, the epsilon p divided by 1 by z e to the power beta epsilon p minus 1. And now when I convert it into an integral, of course the denominator will give me 1 by z e to the power beta epsilon minus 1 G epsilon d epsilon times epsilon. Now I don't have to worry about the ground state contribution becoming infinite when z approaches 1. Why? Because when I'm considering the ground state, surely to the beta epsilon that becomes 1. So I have 1 by z minus 1, and this will diverge when z approaches 1, but then the numerator makes it 0. The contribution of such a diverging term becomes 0 simply because when I'm considering the ground state, epsilon itself is 0. So therefore, I don't have to take out any contribution. Therefore, I can. Okay. So it turns out that there is an interesting relationship between these two quantities, which we will now derive. It turns out that P is equal to 2/3 the average. So we'll just derive it using these two expressions, this integral and this one. So we start with this one and we will go there. Start with this one. This one, what I now do is this term I integrate by parts. So this I take to be the first function and this I take to be the second function. So if I do that, what do I get? I get minus of log of 1 minus a d to the power minus beta epsilon times integral of t epsilon g epsilon to be evaluated between 0 and infinity. This is one term plus. Now I have to take the differentiation of the first. So if I do that, I get 0 to infinity of d epsilon by 1 minus a d to the power minus beta epsilon. And the differentiation here will give me beta. So we get minus a d to the power minus beta epsilon times minus beta times g epsilon d epsilon. First function into integral of second minus integral of differentiation of first into integral of second minus log of 1 minus. Now if I look at this quantity when I evaluate it at epsilon infinity, so when epsilon becomes infinity, this term becomes 0. So log 1 will give you 0. So there is no contribution from the upper limit. Next is what happens when epsilon equal to 0, and when epsilon equal to 0, then this function E epsilon G epsilon. So remember that G epsilon, it goes as epsilon to the power half. So therefore this guy, it would go as epsilon to the power 3 by 2, and when epsilon goes to 0, this term will give you 0. Okay? So either from the upper or the lower limit, you get a 0 contribution from the first term. So therefore the first term I can forget about, and I am left with only the second term. So in the second term, let me just do this integral. Okay, so if I do this integral, what do I get? I know that G epsilon is equal to A epsilon to the power half, where A is B by 4 pi square of 2m by h bar square whole to the power 3 by 2. If so is the case, then integral of G epsilon T epsilon, this would give me 2a by 3 epsilon to the power 3 by 2. What is this? This one is nothing but 2 by 3 epsilon times a epsilon to the power half, and this itself is the epsilon. So you get 2 by 3 epsilon g epsilon. So therefore, this term is nothing but 2 by 3 epsilon g epsilon. So let's just substitute it back there. This term we have already argued becomes equal to 0. So if I substitute it back there, what do I get? This term becomes this term. I just do the substitution there and simplification. So I get that term to be equal to 2/3 beta of 0 to infinity of epsilon g epsilon d epsilon divided by 1 by z e to the power beta epsilon minus 1 minus minus log of 1 minus z. But what is this guy? This guy we had seen just a while ago is nothing but the average energy. So therefore, what I get is PV by kBT is equal to 2/3 1 by kBT. This 1 by kBT is coming from beta here. E average minus 1 by kBT log of 1 minus z. Unless z is very close to 1, as I argued, this term is very small, so it can be neglected. This term is very small unless z is equal to 1. So if z is not equal to 1, that or z is very close to 1, unless that is the case, you can neglect that second term. So if I neglect that second term, it's a very small contribution. So then what do I get? I get PV is equal to 2/3 E average, which is what I wanted to prove. Okay. So then till now what we have done is we have done these calculations for an ideal Bose gas and an ideal Fermi gas. And for an ideal Bose gas, the point was that if you take the energy levels, then any energy level can accommodate any number of particles. There is no exclusion principle. While in the case of Fermi gas, there was an exclusion principle. You are not allowed to put more than one particle on any energy level. And then what we did was we did the computation of the partition function for an ideal Bose gas. Ideal meaning that there is no interaction between the fermions. The fermions are non-interacting, so therefore the Hamiltonian of the system comprises only the kinetic energy contribution. There is no potential energy contribution. We found out expressions for pressure times volume by taking the log of the partition function, the grand canonical partition function, and multiplying it by kBT. We also found out an expression for the average energy of the system. We found out an expression for the average number of particles in the system. And we did these calculations for both ideal Bose gas and ideal Fermi gas. And now what we will do is we will take the ideal Bose gas and ideal Fermi gas both together, and then we will take the limit of very high temperature. And what we will see is that both ideal Bose gas and ideal Fermi gas at very high temperature behaves like ideal gas. So therefore, they will follow the equation of state for an ideal gas. PV is equal to NKV. So therefore, Bose and Fermi gas, these are quantum gases, they behave differently at low temperature, but when you raise the temperature to very high values, both of them behave in the same way, and the behavior is that of an uh, ideal gas. PV is equal to NKV. We will later show that that ideal gas is described by what is known as the Maxwell-Boltzmann statistics. But that we will do later. But at the moment we want to do is to take the high temperature limit of the ideal Bose gas and the ideal Fermi gas and see what we get out of it. So before I move on, let me just ask, are there questions or comments or feedback, anything that you want to uh, discuss or you want me to go over again and so on?
Sir, no question, sir.
Then what we do is that we'll take the ideal Bose gas and the ideal Fermi gas and consider their behavior at very high temperature and see what we get out of that. Expression for this thing was equal to 0 to infinity of G epsilon G epsilon started for Fermi gas minus S for this. And I'm neglecting the contribution for Bose gas 1 by Z minus 1 in the denominator coming from the ground state. This is simply because I'm assuming that Z doesn't have a value which is very close to 1. We will see why at very high temperature Z has a value much smaller than 1. We will see that later. So in fact, we see it right away because Z is equal to e to the power beta mu. So therefore, when you are at very high temperature, the beta is small. So then this is much smaller than 1. And by the way, G epsilon is V divided by 4 pi square of M by H plus square to the power 3 by 2 of epsilon to the power half. So let us divide out everything by volume and see what do we get. So if I divide it out by volume, I get N, which is the particle density. I'm substituting the form of G epsilon here. I get Exact. And now what I do is that I rewrite it slightly differently. So let's just look at this term. This term, I now rewrite it as or half e to the power minus beta epsilon by 1 plus minus z e to the power minus beta epsilon. I can pull this out. So I get this is equal to infinity epsilon epsilon to the power half z e to the power minus beta epsilon of 1 plus minus z e to the power minus beta epsilon minus 1. And now what I want to do is, now since z is much smaller than 1, so I want to do a Taylor expansion on this quantity. So to do a Taylor expansion, I need to do a transformation of variable. So let me do that. I put beta epsilon equal to x, which implies beta t epsilon is equal to dx. So if I do that, then I get n 1 divided by 4 squared. N by squared of 2 of so this just comes out from the substitution here. Take by beta to the power 3 by 2 from 0 to infinity of dx e to the power minus x into square root of x 1 minus plus z to the power minus x plus x square into the power minus 2x minus plus z cube e to the power minus 3x just evaluate that integral. Um, minus 2x square root of x. The third term will be plus z square 0 to infinity dx e to the power minus 3x square root of x. Therefore, you see that I have to deal with an integral of the following sort. can be evaluated by easily. You put nx is equal to y, and then I will be what? I will be just equal to 1 by n to the power 3 by 2 of 0 to infinity of dy e to the power minus y into square root of y. This is just the, you can evaluate it, express it in terms of the gamma function. So what you get is you get gamma 3 by 2 by n to the power 3 by 2. But gamma 3 by 2 is half gamma half, which is square root of pi by 2. So therefore this thing is equal to square root of pi divided by 2 n to the power 3 by 2. So this is for when I have nx. So I need the value for n equal to 1 for the first integral, n equal to 2 for the second, n equal to 3 for the third, and so on. So if I just substitute these expressions back here, what I get is term will give me all the factors of pi outside. So if you do that, then you get this to be equal to 1 by 4 pi square of 2n by h dot square whole to the power 3 by 2 of z by beta to the power 3 by 2 of square root of pi by 2 of 1 minus plus z by 2 square root of 2 plus z square divided by 3 to the power 3 by 2 minus plus z cube by 4 to the power 3 by 2. So this is our final expression for the density. The last line. That is the final expression for the density. So we will write it in a slightly simplified manner by introducing some new quantities. So let's see how does it look like in terms of a new quantity that we now introduce, which is we go with the momentum related to the wave number in terms of this formula. Okay. Which is h by 2 pi, and k is 2 pi by lambda. So this gives me, this is equal by lambda. Because lambda is equal to h by p. Now when you are at temperature T, we are dealing with ideal gases. So therefore, the momentum contribution and the kinetic energy contribution is the only contribution that is there to the total energy of the system. So therefore, I know that p square by twice n, so it's going to be half kVt. Because when you are, the gas is in equilibrium, so when you are in equilibrium, so the average kinetic energy of the system is going to be half kVt for every degree of freedom. So this goes under the name of equipartition theorem. So this we did not have time to look at. But the proof is very simple and you can find it in any textbook. So this one therefore gives P is equal to square root of m kVt. Here, this lambda is equal to h divided by square root of m kVt. So what is this guy? This guy is what is called the Broglie wavelength. This you must have studied in quantum mechanics. So what it tells me is that a particle can have as both a wave and a particle nature. So therefore, if I ask, if I consider a particle that has got momentum p and there is associated with it a wave, what is the wavelength of the corresponding wave? That wavelength is given by the Broglie wavelength, which is given by lambda is equal to h by p, which is what we have found here. So we define a new quantity lambda. Let me call it lambda th. This is given to be h divided by square root of 2m pi kVt. So this is of the same order as the Broglie wavelength. So this is what is known as the thermal wavelength of the particle. Why do I introduce that quantity? Because if I introduce that quantity, then in terms of this quantity, this whole free factor, it writes simply as Z. Let me write it upstairs. This equation, right? Simply Z divided by lambda th whole cube of 1 minus plus z by 2 to the power 3 by 2, whatever I have there, plus z square by 3 to the power 3 by 2 minus plus z cube by 4 to the power 3 by 2 and so on. We already assumed z to be much smaller than 1. So therefore, this expansion, is consistent only if z much smaller than 1, that means lambda th cube n times lambda th cube, that must be smaller than 1. There are questions that things unclear. Go.
Any question? Next. Sir, no questions.
We got an expression for the number of particles per unit volume. Now let's look at the expression for the average energy. And we will derive a similar expression for that quantity also. So what is the expression for the average energy? This is 0 to infinity of E epsilon. 2 epsilon times E epsilon divided by 1 by z e to the power beta epsilon plus minus 1. Again, plus is for Fermi and both for both it is minus. So therefore, if I look at the energy density, energy per unit volume, and use the expression for G epsilon, then I get this to be equal to 1 by 4 pi square of 2m by h per square whole to the power 3 by 2. 0 to infinity of 3 epsilon 7 to the power 3 by 2. And I multiply both the numerator and the denominator by z e to the power minus beta epsilon. So I get z e to the power minus beta epsilon by 1 plus minus z e to the power minus beta epsilon. Again, the idea is very similar. So z is much smaller than 1. So therefore, we will do a Taylor expansion. Taylor expansion here. So what we will do is that first of all, do a Taylor expansion. And the substitution x is equal to beta epsilon. Just as we have done for the average number of particles. If you do that, then this guy writes as beta to the power 5 by 2 of 0 to infinity dx e to the power minus x to the power 3 by 2. And now we have the terms from the Taylor expansion. 1 minus plus z to the power minus x plus z square to the power minus 2x minus plus z cube to the power minus 3x plus the 15. So now we have to deal with an integral of the following kind. If you put in x equal to y, then this integral becomes equal to 1 by e to the power 5 by 2 of 0 to infinity of dy e to the power minus y to the power 3 by 2. So this now writes as gamma 5 by 2 divided by n to the power 5 by 2. But gamma 5 by 2, we know what it is. It is 3 by 2 gamma 3 by 2. And gamma 3 by 2 is half square root of 2 pi. Square root of pi. So if I just substitute it there, so this I get equal to 3 square root of pi divided by 4 into the power 5, right? So now I substitute this expression here. Substitute this expression here and again introduce the thermal wavelength that we have already defined. So there's two lines of algebra. You have to just substitute it there. So the final expression that you get is 3z divided by 2 lambda thermal cube beta 1 minus plus z by 2 to the power 5 by 2 plus z square by 3 to the power 5 by 2 minus plus. And we had already gotten an answer. So this is for the average energy density. We already had an expression for the particle density. So let's just write that. After, the particle density expression was lambda thermal Q times N is equal to Z 1 minus plus Z by 2 to the power 3 by 2 plus Z square by 3 to the power 3 by 2. This was the expression where we have to recall that Z is much smaller than 1. So if you just invert it, you get Z is equal to N lambda thermal Q, and you have to take the inverse of this, right? So if you do that, so you invert it using Z much smaller than 1. If you invert it, you get if you invert it, you get this 1 plus minus Z by 2 to the power 3 by 2 minus Z square by 3 to the power 3 by 2 plus minus, this is what you get on inversion. But now for Z, you can substitute it back from there. Now you substitute Z is equal to what? Z is equal to lambda thermal cube N. Substitute the same quantity again. Because I want to know the leading order correction, I mean the leading behavior of Z. So therefore you substitute it like this same quantity here. In here. If you do that, then to leading order, what you have to do is you have to replace Z everywhere by lambda thermal cube N. Because that will give me the leading behavior. So then what you get is Z is equal to lambda thermal cube N 1 plus minus. Now for Z you can substitute lambda thermal cube n by 2 to the power 3 by 2. This is going to give me the leading correction. Minus lambda thermal cube n whole square by 3 to the power 3 by 2. When I look at the expression for E average by V, which was given to be equal to 3z divided by 2 lambda thermal cube beta 1 minus plus z by 2 to the power 5 by 2 plus x square by 3 to the power 5 by 2 minus like this. And I substitute it there. So what I will get is this will be given by n by 2 beta So I'm just substituting this expression here. So I guess for z I will have 1 plus minus lambda thermal cube n divided by 2 to the power 3 by 2. This is one term. The second term will come from here, which is 1 minus plus thermal cube n divided by 2 to the power 5 by 2 minus double bracket. Now we have already proved that P is equal to 2/3 E average. So E average we know. So when I do 2/3 of this, I get PV. So I get PV. So this will give me N KBT. And if I just expand out this term there, what I get is I get 1 plus lambda thermal cube N divided by 4 square root of 2 plus minus. Yeah, plus this, remember it is for the bulk gas and minus is for the Morse gas. This tells me that both for ideal Fermi gas and Bose gas, when you go to very high temperature, such that Z is much smaller than 1, you recover to leading order the ideal gas equation, plus there will be correction. Okay? And this correction, it becomes smaller and smaller as you increase temperature. Why? Because lambda thermal is proportional to 1 by square root of. So as you make your system go to higher and higher temperature, the correction factor decreases. The correction factor decreases, meaning that the Bose, this factor becomes smaller and smaller. And therefore, the Bose gas and the Fermi gas, they have the same behavior, namely that of the ideal gas. So, are there questions until now?
Sir, one small question. Sir, what happens when the interspacing of the particle is equal to the thermal wavelength
So when the interspacing, okay.
between
Hmm.
between the particles is equal or comparable to the thermal wavelength?
Okay, so that is kind of midway, neither here nor there. When the wavelength and the interparticle, when the wavelength is, the quantum limit corresponds to the case when the wavelength is much smaller than the spacing, interparticle spacing. So then, of course, there is no like overlap, and then you can treat the system classically. So when wavelength is much smaller than the interparticle spacing, then it's a classical. When wavelength is much larger than the interparticle spacing, then it's quantum. And when it is between, what you're saying is what happens when the two are equal, right? So when they are equal, then of course, I mean, you cannot, when I do this truncation, I have to keep all the terms. I mean, it is neither classical nor quantum. Like it has, you cannot treat it like classically. I mean, okay, so let me put it this way.
Okay, sir.
System is quantum. Okay, you are trying to approximate it by a classical way. You are allowed to do that approximation provided your thermal wavelength is much smaller than the interparticle spacing. For example, when the thermal wavelength is much smaller than the interparticle spacing, the interparticle spacing will be 1 over n. So then you are allowed to treat the system classically, while otherwise you cannot do it. When can you treat this as really a correction? When lambda thermal cube n is much smaller than 1, or lambda thermal is much smaller than 1 by n to the power 1/3. Okay, so this is when you can treat the system classically. Because this 1 by n to the power 1, this is the interparticle spacing. If this is the case, then this is like a very, very small correction, and then you uh, recover the classical answer. But otherwise, when the two are equal, and so you cannot do all these expansion. You have to treat the system in full glory. That is, you have to keep every term. You cannot do any expansion anywhere. So this expansion will not work. This expansion works only when you are at very high temperature. So high temperature that lambda thermal has become very, very small. Why? Because as temperature increases, lambda thermal becomes very small. It becomes small, much smaller than the interparticle spacing, and then this is the classical result. Okay, up to some corrections that become smaller. But otherwise, in any other situation, you cannot treat it like this. So you have to treat Bose gas like Bose gas, you have to treat Fermi gas like Fermi gas. You cannot mix that.
Okay, sir. Thank you, sir.
Yeah, other question?
Sir,
Yeah.
sir, what about chemical potential in Fermi gas and Bose gas?
Okay, so this we discussed because for Bose gas, we saw that the chemical potential it can take up in any value between minus infinity and 0. This is for Bose gas. But for Fermi gas, there is no such restriction. Mu can be anything. This we discussed yesterday. And for Bose gas also we discussed it. Why this restriction comes? That restriction comes because we have a factor of the following sort. No? When you are looking at the number of particles in the pH level, you have something like this. 1 by z to the power beta epsilon p minus 1. Okay. So therefore, when you are in the ground state, then this factor, it becomes just 1 by z minus 1. But the number of particles cannot be negative. So therefore, z has to be a number smaller than 1. And z is equal to the beta mu. So it just says that mu has to lie in this range for both. But for Fermi, there is no problem because for Fermi, you get a plus sign. So nothing can be negative there. So z can take any value. And therefore, mu, the chemical potential also can take any value.
Sir, and what the difference between chemical potential and Fermi energy?
No, chemical potential is the
EF and mu.
so Fermi energy is the chemical potential at T equal to 0. This also we did. Take a Fermi gas, you compute the chemical potential at T equal to 0. What you call chemical potential is itself the Fermi energy.
Okay, sir. Thank you.
Yeah. Good. Any other question?
Sir, what happens to the specific heat of these gases at high temperatures?
Okay, so at high temperature, it behaves like an ideal gas. So you get whatever your answer is for the ideal gas, no? Cp minus Cv is equal to R.
Okay.
At high temperature, there is no distinction. It behaves like a classical gas.
Okay, sir.
Okay, any other question?
One more question, sir.
Yeah, please.
Related to thermal wavelength, I am asking,
Huh.
can we measure the thermal wavelength directly in an experiment? Suppose if so, how we can measure the thermal wavelength in an experiment?
I think thermal wavelength, you can make an order of magnitude estimate of it by doing some, you go to very low temperature so that the system behaves like a quantum system. And if you do some interference experiment or some diffraction experiment, so okay, so first of all, what you have to do is that you have to shine the system with a light that has the right wavelength. That is the wavelength of the wavelength equal to the thermal wavelength. Okay, so if you take such a light and shine the system with such a light, and if you get some interference effect, that is one way to measure. I don't know whether historically that was how it was measured, but this is one possibility. You got the point, right? That suppose I
Yes.
want to do some, diffraction, d sine theta is equal to n lambda. So then the lattice spacing, d is like the lattice spacing between the atoms, okay? The spacing between the atoms. And so then that lambda, that has to be chosen to be equal to the thermal wavelength. I don't know how exactly historically this experiment was done, but this is one possibility.
Okay, okay, sir. Thank you.
Any other question?
No, sir.
Okay, so maybe I just summarize, whatever we have um, done until now, and see if we can We can summarize what we learned. So we learned that there is this ideal Bose gas and ideal Fermi gas. So you can say this is my temperature axis. So when the temperature is very close to zero, the two are very, very different. Okay? And now as you increase temperature, the two start to become similar. And they become exactly like the classical ideal gas. When you go to very high temperature. So that is what we learned. So at low temperature, they are different. They will be different at any given temperature. But the difference between the two will become smaller and smaller as you go to higher and higher temperature. So this is what we learned today. So in the next lecture, what we will do is we will discuss the Bose-Einstein condensation, which is an important phenomenon to learn about. And then we will also talk about what is known as the Boltzmann gas. Okay? So this is something that we will do in the later, in the second part of the course. Last lecture probably. You are